Yeah, so thank you very much, Dr. Rizwan Jahangir, for first accepting our request to give a talk at Maths Volunteers. And it's a pleasure to have you here. So, hello everyone. Thank you for joining. So, today our speaker is Dr. Rizwan Jahangir, and he will talk about Hilbert series, polio mean ideals. This is something I struggled with. I asked him, but maybe I didn't do a good job. So you will hear the correct pronunciation from him. So thank you, Rizwan, again, and you can start.
Thank you, Wajid and others. And I also apologize. Actually, I was asked a long time ago to give this talk, and then I had to postpone due to some issues. But thank you for sort of giving me an opportunity to express these ideas to the young generations who can grasp some of it. I will try to keep it as basic as possible so that even the people who are completely new to this field or the masters or PhD students they are studying, they might want to study this particular field. So I will try to introduce basic notations and we will go through some examples, and I will also introduce some of the open problems they might interested to work on. So the correct pronunciation to this is polyomino. So it's like you can distinguish into two words, maybe then it can be easier, polyomino. But when you just say it with the fluency, you can call it polyomino. But it is a combinatorial object, and I'm just keeping it a surprise a bit. I will show you and everybody. I think most of you have already seen these objects. But let's first talk about what a Hilbert series is, and then we can talk about okay, how can we compute the Hilbert series of these specific ideals, or why these ideals are interesting, then we can talk about. I have divided this talk to, as I already said, most of the time we are talking about the basics. So we will talk about what the graded polynomial rings are, then we will go over some definitions, and at the end, some open problems. So to start with the graded polynomial ring, the very first or natural question that comes to our mind is why even we are talking about the grading? And the answers are these three bullets. Like the very first thing, grading help us to decompose them into smaller pieces. So if we want to study it bit by bit, this can help us do that instead of doing it as a whole chunk. And then if we talk about the rings and modules, we can measure a lot of other information that is coming from the combinatorial properties of the associated objects. So somehow what we will be doing is associating the algebra with the combinatorics. So that we can translate the properties that we understand visually to the ones that appears more naturally in algebra. To start with, let's begin with a very basic and specific definition or example of a polynomial ring. Simply, we treat S over a K vector space. So what we have, K is our real field. You can take it real numbers or sometimes integers, or but we are just talking about these are the polynomial. But what we are interested is that elements in this particular ring, how they are being written or treated. So they are just the finite sums of these monomials. We simply call them monomial, and you can understand it. Okay, for example, if I give you an example of k of x1, x2, maybe just a polynomial ring in two variable. More naturally, what we see in our undergrad or other courses, we just use this notation k, xy. So a polynomial ring in two variables. But when we have more than, let's say, alphabets, then it's better to use indices x1, x2. It's just that like naming them. It's not like specifically we always have to use this notation. And these numbers that we see in the powers like C1, C2, Cn, they actually uh, like record some combinatorial properties, which we generally know as degree. We already know them, but we will talk about in the graded structure later. So how do we define grading, which we naturally understand? Let's say even if we are a 10th grade student, we understand, okay, the degree of a polynomial, like usually we knew if I write x squared plus 3x plus 7 or x cube, we understood it like without even realizing what's going on in the background. We say the degree of this polynomial is 3. And the reason is we define the grading on the associated polynomial ring on which we are working for. And this is the natural grading we set. We set each variable to have degree 1. But this is the definition that we set. Of course, in some cases, if needed, we can set different degrees as well. And then there is a whole new theory of shifting, and because once we have set a different grading than the standard one, this is what we call the natural grading or standard grading. But if we set it to different, then what we are interested is to look back, okay, if we want to make some morphisms or other transformations, can we roll back to the standard one? So then we simply say we can do some shifting. And if you have set the degree to be, instead of 1, you have set it to 5, then we just have to shift 5 units so that we can collaborate, or you can say simply calibrate with the standard one. And any monomial, when monomial is simply is when we take the variable and take their product. For example, in this case, when I have written this polynomial, it was a single variable. So monomial is simply x to power some power n. That's what we call the monomial. But when we have more than one variable, like if we have s is equal to k of xy, then a monomial will be some power of x, let's say c1, and some power of y, c2. So any combination in this one, that is what we will call monomial in this particular ring. And same is the case when our polynomial ring has n variable. What we are saying, x1 has some power, then the product with x2 with some power, and so on. And the total degree of this monomial will be then defined by taking the sum of all these powers. So, and that's once again what we understand naturally. One thing I would like to say at this point, any of you or participants, please feel free to interrupt me if something is needing more explanation, or you wanted me to repeat some stuff. You can just interrupt me during the talk. It's not necessarily that you keep your question by the end. For me, it's okay. But I don't know if you follow a strict rule that participants have to ask question at the end. I don't know that. Then we talk about once the grading is set. So what is it? Grading is simply assigning the grade or degree to variable. Because once we have give the grade to variable, because we are saying each variable have degree 1, and then we count how many times the variables are being multiplied. That's all what we are doing here. So then we call the graded component. Graded component are simply we collect the component which have same degree. So for example, 0 degree component, they are just the field element. Sorry, I think. Yeah. So 0 degree element are the elements that are coming from our base field. Because if I involve any variable, then we are already having at least degree 1. And if I multiply it with or take product it with another variable, we are increasing the degree. So degree 0, that's why we simply say is S. S1, we denoted all the elements that are of degree 1. So in our case, if we are setting the degree to be 1 for each variable, then S1 will be simply collection of all our variables. So x1, x2, xn, this will be our S1. And then S2 is all degree 2 component that could be, for example, xi to power 2. That could be 1, like if we take power 2 of each component, or we can take xi, xj product. These are all component, we accumulate them in a set. So I and j, they runs from, let's say, 1 to n. So these are all possible combination, they will come into the S2. And same way we can keep going. We will have S3, all the elements that are of degree 3. And we call it as a graded or homogeneous component. So we use these two terminologies side by side, homogeneous or the graded component. Now, each graded component, actually, it can be viewed as a k-vector space, because we can look at it's a vector space over a field K, and we already got the basis elements. And this is what actually will be the interesting. I'm just setting it a name here, the vector space, and we will use it later. Now, after this, what we will call as a homogeneous polynomial. So the component is already understood. So this is a homogeneous monomial. This is a homogeneous monomial, or because if they are belonging to just one component. So we simply call a polynomial to be, by the way, this is the same thing like we have monomial when we have one and polynomial when we have more. It will be the same structure that we will be talking about polyomino. So simply say, let's say first of all, your polynomial has a certain degree I, and then each component have that degree. That's what we call it, homogeneous polynomial. So if let's say we have S a polynomial ring just in two variable x, y, then we can have a polynomial f of x, y, suppose x, y plus 3x squared plus y square. That's what we will call as a homogeneous polynomial. But then there is a question for the 0 degree polynomial, because what we are saying, this is a homogeneous polynomial of degree 2. Then the 0 degree polynomial, actually it can be considered a homogeneous polynomial of any degree. And this, why we are setting it like this, because what if you remember what I said, each component S1, S2, S3, we will consider them as a vector spaces over K. And for a vector space, we need the 0 element in it. If I just keep, okay, S1 are the only element, these one, X1, X2 up to Xn, then we cannot make it a vector space because we are missing the 0 element. So to make it a vector space, we need to include 0 as a homogeneous polynomial of degree 1. So that is the reason we are considering 0 as a homogeneous polynomial of any degree, so that we can include it into every set S0, S1, S2, and so on. Now, when the grading, so these are the property that are being satisfied for the standard grading. And if we want to just verify, actually these are equivalent property, you can verify one of them. And if any one of the properties being verified, you can simply say the grading is standard. And this is easier. So if you look at the first one, it's still saying you take a component of degree I, you multiply it with the component of degree j, what will you have as a new degree? It's coming from the very basic, when you have a to power m times a to power n, a simple exponent rule, remember that becomes a to power m plus n. So we are doing exactly the same thing. We are taking a degree I component, multiplying it with degree j component, and then the new component that we will have will surely be inside the degree I plus j component. Or in another word, we can say the degree of a product is equal to the degree of the first one plus the degree of second one. Now, this grading helps us to decompose what I said in the very start, like why we are considering given grading. We can decompose each polynomial in a unique way, and we can write it as a sum of graded components. I will show you this with example that would be better. Yes, here. So for example, this one, we have a graded polynomial or homogeneous polynomial, and it is of degree 5. But if you see the second one, it is not a homogeneous polynomial because we have degree 5 in this component, degree 5, but here we have degree 3 and then we have degree 2. So in each component, or let's say in each of its monomial parts, we do not have the same degree, so we are not saying it to be homogeneous. So, but still we have homogeneous components. So we have a component of this polynomial that belongs to S5. We have a component that belongs to S3, and we have another component which belongs to S2. So that's what I was saying previously. Every polynomial can be written as a sum of components from SIs. And this interpretation is unique. We cannot have any other possible interpretation if we want to list it as a sum of components coming from the graded components. Okay. And then if we go to the ideals, how we define the ideals to be graded, uh, if any one of these,
Sorry to,
yes.
you didn't clarify what K is, right?
Carry what?
The coefficients, what are they?
They are coming from K. That's what I said, because these are K vector spaces.
And what is K?
K is base field actually. It's any field we can consider.
It could be Z2, right?
Yeah. But Z is not a field, that's why we ignore
Z2,
it.
Z2.
So yeah, Z2 is fine, but mostly in the books that you will say from commutative algebra, they consider it Q or R. But just to because the finite fields have different properties. That's why we simply take it to be infinite fields. So
But so far,
maybe
whatever you said works for any ring K, right?
it is. Yeah,
Z2.
the definitions are comparable. But the things that we will be, because if we just consider the Z2, then you can see that this is just a zero component. Same is the case, this is a zero component. So that is the reason we try to ignore the, let's say, finite fields. So you can take the best example. We are talking about two fields only, either here Q or R. Now, any other question? Okay. So then graded ideal, if we can verify any of these one condition, we can call them as a, so these are not basically definition. You can say the criteria to check if the ideal is graded or not. So if you take every homogeneous component of the polynomial, and that is also inside the J. So for example, let's go back to the example. Suppose this is one polynomial you find, and this is a polynomial inside our ideal. And if you see each and every component of this polynomial also belong to the same ideal, then we will call it the ideal is graded or homogeneous ideal. The second one is if J can be decomposed like this. So the ideal have the graded component, like we have the graded component of ring. And similarly, if J, the generator of so this is the easiest one. So if you can have an ideal J that is generated by F1, F2, let's say some Fm polynomials, and if all of these polynomials are homogeneous, then we will say the ideal is homogeneous or graded ideal. And this is easier because most often when we are talking about the ideal, we start with their generators. And similarly, if we want to see the grading inheritance in the quotient ring, we will have to have a graded ring S and then the graded ideal I. So then each component of Ri will be simply the quotient of their respective components. Now we will talk about why we needed that K vector space, because then we can talk about the Hilbert series. This is what we have, Hilbert function. Hilbert function is simply a function that is from, let's say, Z to Z. And what it is doing, it is associating each I to the dimension of its graded component. So this is what we have, K dimension of Ri. So what we are doing, first we are considering R as a graded ring. So what we are saying, it has graded component. It has graded component R0, which we already set K. Then it has component R1 that will be the collection of all elements of degree 1, including 0 of course, and then R2, R3. Then what actually we will be doing, calculating the dimension. So dimension of K as a K vector space, that would be 1 because this is generated by 1 over K. Then we have the dimension of this particular vector space over the field K, and same dimension of R3, and each dimension we will call it the output of our Hilbert function. And then using that output and setting up a basically Laurent polynomial series, what we can say, because why we say this is Laurent polynomial and why we can have negative exponents, because if we do the negative grading. But if we are talking about only standard grading, then we have only the t to power 0, t power 1, 2, 3. So what I am saying is, you write first the dimension of K, or K vector space of R, that is your first component. And this is, we already understood, that is 1, plus we will have the dimension of R as a vector space T, and so on. So taking this sum, this is what we will call as a Hilbert series. And now this can, in most of the cases, it can end finitely. And we will see it here. Let's first take one example so that it does not become dry. We have a polynomial ring kxy, and we are talking about standard grading at the moment. And we got an ideal x square y cube, definitely not the graded ideal because the generators are, oh sorry, this is a graded ideal because generators are homogeneous, but each polynomial is a homogeneous of different degree. I think I should clarify here. So for example, if it was x square minus y cube, this would not be a graded ideal. But this is graded because each component is graded. It's not necessary that they belong to the same graded component. Now let's talk about what are the K bases for this particular ring. And now when we talk about in degree 0, it's generated by 1 because degree 0 will always be K. Degree 1, we still have variable x and y. So we have these are the two bases that can generate degree 1. In degree 2, x square will be in the quotient, so that will go to 0. So we are only left with x, y, and y square. So we have two element in the basis set as degree 2, and similarly degree 3, x cube cannot be there because x cube can be simply x times x. Similarly, y cube is already going to 0, and then we have x times y square only that can be here the basis. So x cube goes to 0 in this case, y cube is already going to 0. Then what is left as x square y, that's also going to 0 because x square is in the quotient. Then we had x y square, which is non-zero. We write it as a basis, and then y cube that also goes to 0. When I saying 0, this means 0 of this quotient ring, S quotient J. So if anything goes to the ideal J, then it becomes a 0 of this quotient ring. Now when we want to write, and afterward, like why I did not write the vector space of degree 4, because vector space of degree 4, all the elements, they just become 0. So basically then Hilbert series will be 1 plus how many elements we have in the basis, that will define the dimension. So we have 2, then same we have 2 elements, so the coefficient is 2, we have 1 element and we have coefficient 1, and this is what we got the Hilbert series, or you can call it Hilbert polynomial, but Hilbert polynomial is the name that is set for a different polynomial. I will show you. So this is what we have a Hilbert series of this particular ring. Now we have more common example. If you want to compute the Hilbert series of k of x, where you have only one variable, then the Hilbert series will become naturally 1 over 1 minus t. And if you have n variable, you will have 1 over 1 minus t to power n. And if you want to see in this one, what would be the dimension of k as an SI component, that is simply a basic combinatorial problem, that how many choices we have to make. Because every time the degree 1 component will be x1, x2, xn, and now degree 2 combination, either their self product or the product with the different elements and so on, it can make it this expression. Next we have Hilbert theorem that actually guarantees us that the Hilbert series, they are actually a rational function. So we can rewrite them as a polynomial with the definite degree. We do not go all the way to infinite, and then the denominator is always 1 minus t to power d. Here d is an important, that is simply the dimension of our ring that we are working, and h of t is what we call as Hilbert polynomial. So this is we use as Hilbert polynomial. And when our ring is Cohen-Macaulay, actually the degree of this polynomial also gives us regularity. Okay, I have that slide.
I'm sorry, I think I didn't get to the previous slide. Can you go back, please?
This one?
No, the other one.
This one, okay.
Yeah. Right. Why finitely generated?
There is this proof we can discuss maybe later, but this actually goodness. It will take some time. I can show you the later, okay? But for sure, that's like Hilbert proved it. We do not have to doubt.
But that only works for finitely generated. I mean, the
This one, yes,
you
this is necessary actually. Finitely generated and then standard grading. So these two things.
but that just means the Hilbert series just stabilizes, like it vanishes after some degree.
That's actually what they needed it, because normally we have the Hilbert series, and then they are continuing. But the most interesting things are when we have basically what we are, sorry, I also see message.
Is it not trivial if I take a polynomial? Can you write it as a h times 1 over 1 minus t to d?
It's not, because we have to find still, like, h polynomial is still coming from the dimensions.
If I take a finite, I mean, it's a polynomial.
In this case, if you just take the ring is like x1 to x, and we already saw it, it will be simply 1 over 1 minus t to power n.
Yes, and in the next theorem,
Mm-hmm.
if my R is finitely generated,
Mm-hmm.
that means the Hilbert series is a polynomial,
Okay. So
right?
finitely generated does not mean that we have these finite variables. So finitely generated rings are a different terminology, actually.
Where each R has finite dimension, or R as a whole has finite dimension.
Ri is already has a finite dimension for sure. When we
So
set
R
the
has
gradient,
finite dimension.
because Ri's are k vector spaces and they are of finite dimension. If we look at them, we will have finitely many elements of that specific degree. When we say here the word finitely generated, we are saying our ring itself is finitely generated. So we
Right.
can find generators of R that are finite.
So what would be the Hilbert series for such? It would be a polynomial, right? It's not a series
It will
then,
be a polynomial for sure.
right? And in that case, I can take H to be that polynomials times 1 minus t to the d, right?
Yes, yes, exactly.
So what is the result saying?
The result is saying the same thing that you are saying. So you have, when you will say the Hilbert series, it's like when you take all the possible 1 minus t as a, you have factored it out, all of them, and basically this h of t will be, so this is your Hilbert series, uh, hr of t. So something, when you take out all the common factors and the remaining one which we have as a Hilbert polynomial, so you are taking out all the common, and that's why the d will then become the dimension of R.
But that's trivial, no?
It is not, and it is trivial in this trivial ring, but it's not trivial in non-trivial rings. We will talk about, like, let's suppose
Well, maybe the
when we
theorem is saying something more about the H, some structural property of the H, maybe.
yeah.
Because in this
So
case, you can just
what
pick.
we can do, let me show you one another ring in the polyomino, which is not really the straightforward ring, and it will clarify this thing.
Okay, thanks.
Okay. So we had another question from Kazi, why homogeneous degree having the same for all components? And can you please re-describe on which slide you were asking this question? Homogeneous degrees having the same for all the component. That is for homogeneous polynomial. If you are talking about, if we are talking about homogeneous polynomial, then each component should have the same degrees. And when we say the homogeneous or graded ideal, then we need to take the each generator to be the homogeneous.
Sorry, I think I got it. So you say finitely generated not as a vector space, but as an algebra.
As
That's
algebra,
okay.
not a vector space. Vector spaces are finitely generated already, and vector spaces are Ri's, not the R in itself is not a vector space.
Right, right. Then it's not making the polynomial Hilbert polynomial finite. It's a K-algebra, so it would go away for long. Okay, I got it. So it's not as a vector space, but as an algebra.
Yeah,
Okay.
but it will be a polynomial finite. That's theorem actually interesting. So
Right,
this
right.
is
Now I
what,
see. So there is the structure of H.
yes.
Interesting. Yeah, thanks.
And this is what I said, when we have a Cohen-Macaulay ring, then the degree of our numerator will also give us the regularity of that ring that we are talking about. But let's talk about the polyomino ideal, and we will see more about this Hilbert series, that how basically the structure of our numerator is being developed from the combinatorics of polyominoes. To describe this, I know like even this name was new to all of you, so let me give some basic definition first. Polyominoes, these things you might have seen in your life, playing games or other, somewhere at least. So these are simply, when we say the mathematical definition of polyominoes, these are the squares, they are joined edge to edge together. So when you just join two squares from the edge, you make a domino. Then you join another one, is trimino and tetramino and so on. And that's what we call as a polyomino. And if we look from the combinatorics perspective, they appear long ago. We can look them as prompt chessboards. We can see them in tiling problems and enumerations. But from algebra point of view, their study started in 2012 actually, when the first paper by Aisha Sloop Qureshi, which is also my PhD supervisor, she studied the algebra associated to these combinatorial objects. And the algebra that she assigned, it was what we call as polyomino ideal. To start with the polyominoes, we take an interval, or let's say uh, you take two elements in Z2. Suppose this is the element Mn, or A comma B. And you take another element, let's say this is ij maybe, and then you take each and every, because when we are talking about z2 we have integers between these elements, so the collection of all these integers in between two elements, that's what we call as an interval of z2. It's the same as if you talk about interval in R2. But now we are just picking the integers, not all the values among those integers. And if we have there's strict inequalities between the boundaries, then we call it as a proper interval. And if we have just one step interval, that's what we call as a cell. So if you start with any point A and your right side point is simply, or the other end is A plus 1 comma 1, this is what we call as a cell. But as I said earlier, we are just interested in the corner, but it's good to join them so that we can look at their edges as well. But since we are in Z2, these lines are actually not what we are considering when we are talking about the interval. We are just picking those points. Now, these 4 points we call as a vertex of our cell, and the lines that are actually not inside the Z2, our domain, we call them as an edge set of a cell. Now, the defining edge is important because the definition of polyominoes purely lies on the connection through the edge. So when we define the polyomino, we consider first a non-empty collection of cells in Z2. So you take one cell, another cell, and that's the first consideration. And second is, what will be the vertices of that collection and edges of that collection? Is simply we accumulate all the vertices of the cells and accumulate all the edges of those cells. We call it as the cells of collection, or the rank of this collection will be simply how many total cells we have. So in easier way, you can say how many squares you have. And then all those corners, then we can, if they are joined, of course, for example, like this, we will have vertices only 6, not 8. So that's important. And also the edges, we have 1, 2, this edge will be counted only once. And the most important definition is how do we call two cells are connected. Two cells are connected if we can find a sequence of cells in between such that each two adjacents are connected through edges. So I think there's no figure, I can show it to you. So for example, I make these three cells only. So suppose this is our cell 1, 2, 3. We can see that cell 1 and 3 are not connected, and similarly cell 2 and 3 are not connected with this definition. Although we can see there is a connection which is through the vertex, but we cannot reach from cell 1 to cell 3 using a path of cells that each two adjacents are connected through edges. So that's why we will call it as weakly connected basically. There is another terminology for this one, weakly connected. Because still we have a connection, but that is through the vertex. But if you have a collection like this, that is completely disconnected. But if all the cells are connected through edges, then we call it a connected collection of cells. And basically, the combinatorial definition of polyomino that we have a connected collection of cells. The weakly connected and the non-connected, they are not termed as polyomino. Okay, this is I already explained. We can look at further this one. So if we talk about, we say this is a polyomino, which is collection of cells C1 to C5 on the left side. You can see that there is, if I talk about an interval, so suppose we start this interval A to B. A to B interval contain these 4 cells in it. And there is one cell which is not inside our collection. So that's important. I will describe why when we talk about the proper interval and like the interval, this is not an interval of our collection, but there is a one cell that's outside of collection. But if you look at the connectedness, C1, C2, C3, C4, C5, you can go from one cell to any other cell using a path of other cells which are each two adjacent are sharing an edge. So this is a connected collection of cells and we have a polyomino, its rank is 5. On the other side, we have a weakly connected as I described earlier. Now comes like if we are able to understand the definition of it, now let's talk about how do we associate an algebra. So we have a non-empty and finite collection of cells. Then we consider a ring and its variable are indexed through the vertices of our polyomino. So suppose, let's say we talk about only these 3 cells. So if our vertex, this is vertex A, B, C, D, E, F, G, H. So what we have a polynomial ring KXA to XH. Now keep in mind, each of these vertices, they have double index because they are in Z2. So we will have their first and second component as well. So that's why you can also see that these index, they will be like the double index. Then if you look at the previous example when I talked about the interval inside our collection or completely not. So let's go back just one. This interval A to B, it's not inside our polyomino. So if polyomino is P, then AB is not inside P. But if you look at the interval AC, that is clearly inside P. So what we call as an inner interval of our collection, if all the cells of that interval belong to collection, if there is any cell in the interval but it does not belong to our collection, we will not call it as an inner interval. So that's what we have I think I didn't mention, yes, we have this definition of inner interval. If all of the cells of an interval, they belong to our collection, we call it an inner interval. And if we take any interval, of course, interval will have, if I make interval, then I will have two other corners as well. And we call these as a diagonal. So if these are our interval AB, and the other two corner, we call them anti-diagonal. And we associate a binomial, which is xa and xb, product of the diagonal entries minus the product which are associated to anti-diagonal entry. Now clearly that's a binomial, and it is a homogeneous binomial of degree 2. So if I generate an ideal, that will be a graded ideal as well. So this is what we call as any this binomial which is associated to an inner interval, we call it as inner 2 minor, and the ideal generated by these two inner 2 minor is called polyomino ideal. Okay, this is the same thing I described to you, that AB is not an inner interval while AC is an inner interval. And this is the notation that we use, IP, for the polyomino ideal, and that is the ideal that is generated by all those binomials. And the quotient ring that we are more interested will be S quotient IP. Now, since we are already clear that our ideal is graded, our S polynomial ring that is associated with the vertices of these polyomino, that's also graded. So what we will have this as a quotient ring, we are talking about a graded ring, and we will be more interested in talking about its Hilbert series. But the natural question that arises in the beginning, okay, we found an ideal, what are more interesting things to do in 2012 if we look back, like when these ideals were defined for the first time? The main focus at that time was talking about the primality, like when these ideals are prime. Because talking about the binomial ideal and proving it to be prime is not, let's say, straightforward or easy job, uh, because we know that the only prime binomial ideals are the toric ideal. And when we can find a homomorphism between them or isomorphism between them, that could give us one idea to prove by. And then there is the new question arrive, can we check if they are radical? Then we can compute their Grosvenor basis, minimal free graded resolution, talk about their regularity, and see when they are normal, Cohen-Macaulay or Gorenstein. These were the initial questions that were being addressed for these particular type of ideals at that time. And to start with the primality, the very first thing that started was distinguishing or dividing these collection of cells into two partitions, one as a simple and the other as non-simple. In rough ways, you can understand if there is a collection of cells and it has a hole in it, it's a not simple. And if there is no hole in it, it is simple. I tried to make the square actually, but I think some issue with the rendering of latex, it made it filled, but it's more understandable that there is a hole inside it. So we have these cells in our collection, but there is one cell inside the collection which is not part of our collection, and we cannot go out of it. But this is non-simple, even though we have a cell which is not part of our collection and it is inside, but we can still go out from that cell. So that's what we call as simple and non-simple. And after this partition, actually, this class of cells, which is simple polyomino, they were proved to be prime. So any ideal or polyomino ideal associated to simple polyomino, it was prime. And the result can be found from these two papers. I think I can now just list them all together. So these are all noun cases of
I'm
prime.
sorry, I didn't see the result.
Which one? Result. Okay, I can
Like,
reshow. So that was simply saying if we have a simple polyomino, then the associated ring has not only prime, it is normal, it's causal, it's also Cohen-Macaulay, and we can even
all right.
find the dimension as well.
Okay.
So this word, when it is a domain, as quotient type is a domain, that clearly says that the quotient, the ideal that is in the quotient is prime.
Okay. Nice.
And this was actually a lot of series of papers proving different collections of cells as a prime. The very first after the simple was the row convex. Row convex, you can understand it as if there are two cells in a row and all of the cells in between should be in the collection, then it will be a row convex. Other, if any cell in the collection is missing, so for example I make this collection in this way maybe, and then I make like this. Suppose this is our collection, so this is not a row convex because these two cells are in the row and they are missing one cell in between. So any collection which is row convex, it is prime. Then simple polyomino was already proven. There is a balanced polyomino term, which is if you have, actually it is a subclass of simple polyomino. And these two paper were the same, actually this is the same paper. So first it was proven for the balanced, it is subclass of simple, and then it was even proved for the bigger class of simple polyomino. But more interesting result came from this paper 4. What are the subclasses of non-simple polyomino? Means the polyomino which has holes inside, they are also prime. So the very first thing was if the hole inside is convex. Now we are talking about both convex, row convex and the column convex. So if you describe the hole inside and the hole is convex, it is prime. Then there was another terminology, grid polyomino and thin polyomino. Then the polyomino if they have quadratic Grosvenor bases and zigzag walk. Actually, I there are, you can find these papers if anyone is interesting to like talk about and write to me if you have more questions. But more what I wanted to show is the Hilbert series actually. But these are all paper talking about how the primeness was there. Now, to talk about the Hilbert series of this one, an interesting phase came in this research area was the Rook polynomial. Rook polynomial is also basically widely discussed in the combinatorics, and there are a lot of results that are proven so far, and they say the Hilbert polynomial, the numerator of the Hilbert series, that is exactly the same as Rook polynomial. And Rook polynomial is easy to understand from the perspective of combinatorics. I will make it quick. So this is what we have. Suppose you have a polyomino. We can consider it as a pawn chessboard. And rook, if someone does not like know about the chess rule, so rooks can move either horizontal or vertical. These are the only two moves they can do. So we say two rooks are non-attacking in a polyomino if they are in a different row or column. So for example, this rook r1 and r2, they are non-attacking because if they move in any direction. And even if we consider this as r3, so r2 and r3 are non-attacking because they do not have this place to move. So this is a little bit different than the standard chessboard. We are talking about prone chessboard because if there is a hole inside, they cannot travel through the hole. So these are non-attacking rooks. And then we call a rook configuration that if I call like one rook configuration is how many times you can place one rook which is non-attacking. That will be of course the number of cells. You can place one rook in one cell it's not attacking any other, you can place in another cell, and that will be the number of one rook configurations. To this is what we are saying as four rook configuration. Like I can place four rooks, and these four rooks are non-attacking. So this is one way. Then we will have another way of putting four rooks that are non-attacking. We will have another way. So we are counting these k rook configurations actually. And these number of counts gives us the rook polynomial. And what we do, we neutrally set this R0 to be 1, that no rook place, we just say 1. And then R1 is the number of one rook configuration, that is number of cells. And then we count how many possibilities are to place two rooks that are in non-attacking position, how many possibilities are to place three rooks which are in non-attacking position, and so on. And then we define a new polynomial whose coefficients are basically coming from these countings. How many times we can put k rooks and they are non-attacking. And this is what is defined as a rook polynomial. And later, a result in 2020 came out that if we have an L-convex polyomino, then the regularity will be exactly as the degree of rook polynomial. And if you remember, previously we said regularity is actually the same as degree of H polynomial. But what is the L convex? I will describe it from the picture. So if you can go from one cell to another, taking at most two turns, that is what we call as an L convex, that is two convex. And if you can go from one cell to any other with at most one turn, this is what we call as L convex. So this type of polyomino, their Hilbert series or Hilbert polynomial was described as the rook polynomial. And then there was the new terminology that was also used for primality, simple thin polyomino. Thin polyomino means like you have only one layer of the cells. I can describe like this. So you cannot have a tetramino inside. You will have only these cells going on. So you cannot join four cells together. So these type of polyominoes are called thin polyomino. And we also had the same result that the Hilbert polynomial, which is the numerator, it's the same as the rook polynomial of this one. And then later, I know I'm going over time, just give me 2 minutes. I want to end this one. I'm sorry. Uh, Later, there was these were the only two results for which the rook polynomial was true in case of Hilbert polynomial. Then what we observed was like there are some position of rooks, they are possibly to interchanged. So for example, I can go back to, so in this one even, if I put rook 1 here and rook 2 here, it is almost the same way if I just put the rook 1 here and rook 2 here. So these two configurations are identical in a way that what we are doing, we are just using different corner. So this was what we defined as switching rooks. So two rooks, they can be switched if they are in the corners of an inner interval. So if you look at the definition switching rooks, we will have now what we are doing now, we make some equivalent rook configurations and we calculate those equivalent possibilities only. So basically now the number of possibilities are reduced so that we are not counting them twice, and we found a new polynomial which is now we called as switching rook polynomial. And this polynomial actually now have been proven for many classes of polyominoes, that this gives us the Hilbert polynomial. And interestingly, if you look back to the previous result, this case was proved for the simple one because thin polyominoes are simple. Even our previous one, when we talk about L convex, that was also subclass of simple polyomino. But this result, after coming up for the switching root polynomial, we had even some classes of non-simple polyomino that their Hilbert's polynomial is the same as switching root polynomial. The very first class is parallelogram polyomino. Parallelogram polyomino is once again the subclass of simple polyomino. If you want to understand it, it's like you have the staircase on both sides. That's what you can understand as a parallelogram polyomino. So in parallelogram polyomino, we had the same result, that their Hilbert polynomial is switching root polynomial. And at this point, Rinaldo, Romeo, and Qureshi, they even came up with the conjecture that for any simple polyomino, this should be true, that the numerator of Hilbert series should be equal to the switching root polynomial. And we started, me with an Italian colleague, we started proving this conjecture, and we end up making another conjecture that this is also true for non-simple as well. So not only for the simple, for any polyomino actually, we have not found any counterexample so far. So we pick any polyomino, we try to find its Hilbert polynomial, and it turned out to be the Rook polynomial. We actually defined a frame polyomino. Frame polyomino is sort of non-simple polyomino where you have a parallelogram whole, and we proved for this one also. uh, these are some results that linked us to go to the end result. I can show you the end one, what we achieved. This one, that for a frame polyomino, the h polynomial, which we have the numerator of the Hilbert series, that's also the same as switching root polynomial. And at this point, we also, of course, regularity is also the dimension. So regularity is the maximal rook that you can place. So we gave the conjecture that now this should be true for any polyomino. And if we talk about the open problem and somebody is interested, the very first is about the prime, that this zigzag walk actually was groundbreaking result. It's from three Italian researcher, and they proved that this is a necessary condition, but we also believe that it is sufficient. So we are trying to prove, but still there was no proof. That's an open. The second, this is a conjecture that all polyomino ideals are radical ideal. We haven't seen a counterexample, but we were not able to prove it yet as well. Third open problem is all of these are Cohen-Macaulay as well. And the fourth one, that the last conjecture is this true for every polyomino. The switching root polynomial gives us the H polynomial. And the last one, or interesting these days, people are working in this particular field, is finding the regularity of the powers of polyomino ideals. So we can take about their I2, I3, and then talking about what are the bounds. All right, if you have any questions, please feel free to ask, and I'm sorry once again going over time.
No, that's okay. And thank you very much and for the excellent talk. And you also give like a nice path of how this area developed and some open problems as well. So yeah, the floor is open to questions if anyone has any questions. So feel free to let me maybe make that change so that they can unmute themselves.
Yes, you can let them unmute if
Yeah,
they are
so
interested.
anyone either raise your hand or put in chat or directly unmute yourself.